Ideal gases. In the combined gas law, P1V1 over T1 equals P2V2 over T2, the amount of gas does not vary. If we need to calculate the number of moles of gas, we need a new variable. We're going to call that N. So N is the number of moles. The ideal gas law is PV equals nRT, where R is the ideal gas constant, and R tells us that volume has to be in liters, pressure is in kilopascals, temperatures in Kelvin, and N is moles. So let's look at some examples with the ideal gas law. It says when the temperature of a sphere containing 685 liters of helium is held at 621 Kelvin, the pressure is 1.89 10 to the third kilopascals. How many moles of helium does the sphere contain? So we have the ideal gas law. If we're solving for N, you could do some rearranging here. Divide both sides by RT. And we get N is equal to PV over RT. Plug in the variables that we know. Pressure, 1.89, 10 to the third kPa. V, 685 liters. Divide all that by R, which is 8.31 units, liters, kilopascals per mole Kelvin. And then temperature, 621 Kelvin. Your units, everything should cancel out except what I'm looking for, which is moles. It's down here in the denominator of the denominator. So when we solve, moles will be my unit. The number of moles comes out to 251. Let's look at this next example. We have N, we have P, we have T. We're looking for volume. So we have PV equals nRT. I want to get volume by itself. So we have volume equals nRT divided by P. I like to rearrange it first. So we have N.16 moles, R 8.31 liters, kilopascals over mole times Kelvin. Temperature is 23 degrees Celsius. In Kelvin, you add 273, so 296 Kelvin. Divide all of that by pressure in kilopascals, which is 101. So you can cancel out your units. Make sure we're ending up with the right units, which is liters for volume. So my volume, it would occupy 3.9 liters. Okay, this next example, you'll notice that we are given volume, we're given pressure, we're given temperature, we're given molar mass. And we want to find how many grams. There's a variation of the ideal gas law that looks like this, where small m stands for mass and capital M stands for molar mass in grams per mole. This is the ideal gas law, but anytime you're given mass in grams and molar mass, this is the one that I would prefer to use. So I want to solve for mass. I want to solve for grams of air. So I like to rearrange this equation up here first to solve for m, the small m. And so I would do some algebraic rearranging, and this is what it would look like if I'm solving for mass. So I take my pressure in kilopascals, 102, my volume, and my molar mass, 29 grams per mole, divide by RT, R 8.31 liters, kilopascals, mole, Kelvin. And temperature is 37 degrees Celsius, which would be 310 Kelvin. If I have this equation rearranged correctly, I should end up with grams. So everything else should cancel. Cancel your Kelvin, kilopascals, liters, and mole. So always go back and check, make sure you have it rearranged correctly. Everything should cancel except for the unit that you are looking for, in my case, grams. So from this variation of the ideal gas law, I get my mass as 2.53 grams. We're using the ideal gas law, and ideal gas does not exist because an ideal gas would have to obey all assumptions of kinetic theory. Real gases have volume, and there are attractions between the particles in real gases. However, at most conditions of temperature and pressure, real gases behave like an ideal gas. So here's the gist. We can use the ideal gas law, PV equals nRT, for any gas at most conditions of temperature and pressure.